Okay, good day. This is AP Calculus. I am Mr. McCully, and this is the presentation on section 4.1, Antiderivatives and Integrals. Now, we are moving into basically the third phase of calculus. The first phase was limits. The second was differentials and derivatives. And this third phase is definitely going to be integrals. Now, we are not going to dismiss limits. We're not going to dismiss derivatives. Those things don't disappear. We definitely need a very strong background in all of those topics to move forward. Today we're going to be talking about writing the general solution of a differential equations. We're going to use a definite integral notation for antiderivatives, and then use the basic integration rules to find antiderivatives and find a particular solution for differential equations. That's what we're looking to do. So let's jump right into it and talk about the antiderivative and the integration process. And basically what it says, and I'm going to go over this definition here in a second, but the antiderivative is the opposite of the derivative. And so it's basically the backwards operation of differentiation. And so some function capital F is the antiderivative of some function lowercase f on an interval I if the first derivative of the antiderivative is the original function for all x in that I. So we get some notation for antiderivatives. This is our differential form, and again, that's why we did differentials as the last section of differentiation in chapter 2. We see this form here, the integral notation. If I take the integral of both sides of that thing, if I take the integral of dy, I'm going to get just y. And then this, and I suppose I should have this first, but this symbol here is the integral symbol. And so anytime you see this symbol, you know that you're going to do the process of integration on whatever comes left with respect to the variable that is dx there at the end. And so the integral of this function f is the original function plus some constant c that we'll talk about here in a moment, just to get a general idea. The general solution versus a particular solution. Since the antiderivative of a constant is zero, I said that wrong. Start over. Since the derivative of a constant is 0, then the antiderivative is an indeterminate form. We don't know what that form is, called the indefinite integral. All right, so whenever we do an integral, we have to add some constant c that we either have to have a placeholder for, or in the case of an application problem, we have to actually find. All right, and how does that work? Well, let's say we want to take the derivative of this function right here. So if I take the derivative with respect to x of y equals x squared plus 4, well, that derivative is just 2x. And note that the constant of the derivative of this constant is 0. Okay, so I've lost this 4 and I don't know what it is. Now come down to here. If I want to take this integral of just 2x, well, I'm only working on this place right here, on this 2x, and I don't know what this is. I mean, we do here because we started with the derivative, but if I was just given this, I wouldn't know that there was that 4. So we put this c in as a placeholder. And since we know that the derivative of x squared is 2x, the integral of 2x should be x squared. Right? So we have to add a constant to hold the place of a constant from whatever the original equation is, or whatever the constant from the original equation is. Now, sometimes that constant is 0 and we won't need it, but you still have to put it in there every time. And again, just like when we were doing limits, I said you had to write the limit every time. If you're doing an indefinite integral, without fail, you need to put a c in. If you don't put that c in, it will be -1. So just a little bit of error analysis. All right. If you forget this constant c, you're going to get a -1. All right. So let's talk about some simple integration rules. And a lot of these are very similar to the ones for differentiation. And that should make a lot of sense because um, anti-differentiation is the opposite of or differentiation. So a lot of these rules. So if you have a constant, if you're taking the integral and you have a constant times a function, you can move that constant out. We do have a simple power rule for integration. It is the reverse. And so remember, if we did differentiation, so if I said d over dx of x to the n, it became n times x to the n minus 1. Well, this one, if it's x to the n, well, the reverse of that, instead of subtracting 1, we're going to add 1. Instead of multiplying by n, we're going to divide by n plus 1, and then we're going to add that constant c. All right. And then the sum and difference rules. So if you have the sum of two functions, you can take the integral of those two functions, either added or subtracted individually. And again, there would be a constant for both of them. I would suggest that you just put 1c at the end. That would constitute a value for both of those. You don't need two separate constants. So there are some basic integration rules on page 250. They are very important. You're going to see here, especially some of the trig rules. The trig rules are all on your you must know it cold sheet. And I'm going to refer back to this page later. So if you got your book handy, you might want to have them, but I am going to write them down before we do them. And so some particular solutions on initial conditions, that's certainly an example. What you want to do is, you might want to look at example number 7, and then that'll give you an idea of what they mean by using an initial condition to find a particular solution. And so let's talk about a simple example here. Well, I'm just going to do an integral of 13 minus x with respect to x. So we're integrating with respect to x. We're going to, and again, not going to do all of these steps each time. I can set, since this is a difference, I can do this as the integral of 13 dx, and then minus the integral of x dx. And so the integral of just any value, in fact, what I might even do is rewrite this so that it is 13 integral of dx, and the integral of dx is just x, so I get 13x. And then this is to the first power, so the simple power rule will say that I'm going to have a half. Actually, you know what? Let's do it just like it. It'll be x to the 1 plus 1 all over 1 plus 1, and do it in 2 steps. And again, I must add some constant c. So my final answer, 13x minus, well, 1 plus 1 is 2. That gives me my half, x to the second plus some constant c. And that is my final answer to that particular integral. Okay, another example here. This is page 255, number 10. They ask you to rewrite, integrate, and simplify. And you're going to see this a couple times, especially in today's stuff. We don't have a simple power rule for this 1/4 or for values of x in the bottom. And another thing we should also remember is there is no quotient rule for integrals. There is a quotient rule, the ho-de hi minus hi-de ho all over ho-ho. There is a quotient rule for derivatives, but there is not one for integrals. So if you get a division here, you're probably going to have to do some rewriting to get it into a form that you can use. So this one is fairly simple. I'm going to rewrite this one as 1/4. There's my constant. I'm moving it out to the front. Integral, well, 1 over x squared can be rewritten as x to the -2 dx. And now I'm going to integrate that using the simple power rule. So I'll get 1/4, and then it is going to be, let's see here, it'll be x to the -2, and then I'm going to add 1 to it over -2 plus 1, like that. And then again, we need some constant out on the end. Now you can put it on the inside, but when you multiply 1/4 times a constant, it's 1/4 times some constant. I don't know what it is, and I don't know what this constant is, so it doesn't really matter. All right, you're going to see me say that a lot. It's just a constant. I don't know what that constant is. If you want to say it's 1/4 times that constant, that's fine. It's still a constant, so it doesn't matter. All right, so let's simplify this thing. I'm still going to get x to the negative 1. So I'm still going to leave a 1 over here. It becomes x to the negative 1. I have a negative 1 on the bottom here. And so negative 1 times 1/4 gives me 4, and then I'll negative, and I screwed that up, and you guys are all saying, McCully, you're stupid, and you are right, because when I move this negative 1 to the, because it's x, to the negative 2 plus 1, which make it x to the negative 1, and when I move it to the bottom, I no longer need that negative 1, and then I need my plus c, or it's minus 1, and that is an answer that I'm happy with. Okay, let's move on to the next one, see if we can do it without making mistakes. And again, hopefully you guys are seeing me make these mistakes sooner than I'm seeing them. And we'll get them all correct when we get to quizzes and tests and the final AP Calc test. Okay, so this thing here, again, there is no quotient rule for integrals, so we're going to have to rewrite. So the first thing I want to use is I want to say that if I have a plus b over c, I can rewrite that as a bunch of fractions. I can make it a over c plus b over c, just like that. I'm going to do that with all of these, and my first rewrite is going to be x squared over x to the 4th plus 2x over x to the 4th minus 3 over x to the 4th, all dx. All right, and then I'm going to simplify all of these, and then, so this first one will be the integral of x to the negative 2, and then this one will be plus 2x to the negative 3, and then this will be minus 3x to the negative 4, and that's dx. And then I'm going to apply the simple power rule, and again, I'm going to use that constant multiple rule tool, but I'm going to start skipping some of these things. And so this thing becomes x to the negative 2 plus 1 over negative 2 plus 1 plus 2 times x to the negative 3 plus 1 all over negative 3 plus 1 minus 3 times x to the negative 4 plus 1 all over negative 4 plus 1, and then all plus some constant c. And let's see here. So this becomes negative 1 over 2 plus 1 is negative 1, so over x. And then I get plus, let's see here, I'll get, it's not going to be plus. Let's do it before we write this. I've got positive 2, and I've got negative 2 on the bottom, because negative 3 plus 1 is negative 2. So I've got 2 over negative 2, that's negative 1. And so we'll make this negative, negative just 1 over x to the negative, or to the positive 2 on the bottom. When I push to the bottom, I see I screwed it up. This one here, let's see, I get negative 3 on the bottom. I've got negative 3 out top. Negative 3 over bottom. Negative 3 is going to be positive 1, so it's going to be plus. And it's going to be 1 over x to the negative 4 plus 1 is negative 3. When I push it to the bottom, it becomes positive 3 plus some constant c. Now, this is fine for an extended response question, understanding that you could have the potential to have to combine this into a single fraction for a multiple guess type question, and then you'd have to find a common denominator, and the least common multiple of x squared, and x to the third is x to the third. And so I multiply, well, I'll just do it. I get 1 over x, so that'll be times x squared over x squared minus 1 over x squared times x over x, and then minus 1 over x to the third, it should be plus, then plus some constant c, which will give you a final answer. So we'll put a big or, x squared minus x plus 1 all over x to the third plus some constant c, and that would be our final answer. So either of these are okay. This is probably your multiple guess answer. But this is usable, so it's good enough. So if I say find the integral on a quiz and you give me this, that's good enough. Understanding that if it were a multiple guess question, they're probably going to combine it into a single fraction. All right, getting down to the end. How's my time doing? Oh, not too bad. We're not even 20 minutes yet. So find the definite integral of. So we've got some trig functions here. First thing I'm going to do is I'm going to distribute. So I got the integral of secant y tangent y minus secant squared y. Now this is all dy, and just notice y's, okay? If they give you y's, since they're, well, let's write it down. Since we are given y, we should use y as our variable. Especially in your extended response questions, unless you redefine it. So, what's the integral of secant y tangent y and secant squared y? Well, here's the thing. We want to go back to page 250 in the book for basic integral rules. And we could break these down into sine and cosine and do them that way, but the more of these basic integral rules you know, the better your life is going to be. And so if you look on page 250 down near the bottom, they have a bunch of trig rules. And one of those is secant x tangent x dx is just secant x plus some constant c. That's one rule. And then another rule they have is secant squared x dx, and secant squared x is just tangent x plus some constant c. So I can break this thing up here into two separate integrals. I can say that this is the secant, let's do it right, secant y tangent of y dy minus the integral of the secant squared y dy. And again, I know that secant tangent is just secant x. So this becomes a secant of y minus the secant squared of x becomes tangent x, tangent y because we're using y, plus some constant c. Now I know I had two constants here. This constant is different than these two. It is the sum of those two, but I don't know what it is anyway, so I just made it into one constant, and we are finished with that particular set of questions. All right. So that brings us to the end, the Star Wars fun fact of the day. There you see Dennis Muren back in 1976. There weren't special effects capable of doing what George Lucas wanted to do with Star Wars, so he hired this guy named Dennis Muren to create ILM, and since then he has been nominated for 32 Academy Awards in special effects, and he is 129. And some of his other movies are other iconic movies like Jurassic Park, Terminator 2, E.T., others like Young Sherlock Holmes, which featured one of the first fully articulated CGI characters. It was a stained glass guy, which was pretty cool, and other great movies like Willow and The Abyss. So all of that CGI stuff, this guy had a hand in creating. Well, that's all I got for today, folks. I will see you in class. Have a great day. Goodbye.